Hi guys, this is a vodcast going through a review of surds. Some of you will have seen them in Year 9 Advanced, others may not. So here we are, we're going to go through what irrational numbers and surds are, and adding and subtracting surds. Okay, the first thing you need to know about surds is that they are irrational numbers. That means that if you have a number under a square root and it can't be simplified as a whole number or a fraction, then it's known as an irrational number, which means that it's a decimal that goes on forever and it doesn't have a recurring pattern, like the pattern doesn't repeat. Conversely, a rational number is any number that can be written as a fraction, where P and Q, P is the top number, P is the numerator, Q is the denominator. They're both integer values. If written as a decimal, it will terminate or it will have a recurring pattern. So, for example, 3 on 4, that is 0.75, which means that it terminates, it stops. 1/3, that will have a recurring pattern of 0.33, etc. An irrational number is a number that can't be expressed as a fraction. It will have a non-recurring pattern that goes on forever, so it doesn't terminate. So we have a look here, 1.5, we can express that as 3/2. So that's rational, because I've got two whole numbers in a fraction. Pi, it's not any, like it can't be expressed as just one fraction over another. They've got approximates, so a lot of the times they approximate pi to be 22 on 7. However, it's not exact. So that's why it is irrational, because it's a non-recurring decimal that goes on to infinity. So that's what an irrational number is. Okay, a surd is a number where we take the nth root of a number and it does not simplify to get rid of the root. The root, the sign is otherwise known as, you can also call it a radical. And you can have like the 5th root or the 3rd root. And when I simplify it, it's not a whole number or a fraction. It will become a non-terminating decimal. So it doesn't have a pattern. And it is an irrational number. So here, which of the following are surds? Well, square root 9, we know that 3 times 3 is 9. So that's not a surd. Root 2, well, you can't square root 2. So that is a surd. If you put it into your calculator, you'll see that it's a decimal. So that's a surd. Root 27 doesn't square root perfectly. So that's not a that is a surd, sorry. So that is a surd. 49, we know that the square root of 9 is 7 times 49 is 7 times 7, so that's not a surd. The square root of 16 is 4, so that's not a surd. 24, we can't square root that perfectly, so that is a surd. Okay, so these numbers here, they cannot be given as a fraction or a whole number. They will be decimals with a non-recurring pattern. So they're known as irrational numbers, and they are surds. Because if you want to display them exactly, they're going to have a square root over the top of them. Okay, here, approximating surds. So what I've done is I've got a table of values. These are 1, 2, 3, 4, 5, 6, 7, 8, 9. And then the numbers below are the square of those numbers. So these are perfect squares. So if I square root 16, I know that I get 4. If I square root 49, I know that I get 7. So it's just a table of numbers and they're perfect squares. Now, we can approximate. A lot of kids, they're impressed when I go up the front and I say, okay, what's the square root of 27? And I say, I think it's about 4.8. And they're like, how would you know that? You don't have a calculator. Well, if you have a look here, no, it's not about 4.8. I stuffed that up. Okay, so 27 is larger than 25. So it's going to be between 5 and 6. But 27 is closer to 25. So let's say it's about 5.2. Okay, so it's somewhere around here, 5.2 to 5.3, I reckon. Root 47, we go here. I know that 47 is closer to 7, So I'm going to say it's about 7.9. We'll say 7.8 to 7.9. Of course, it's not exact, but it's pretty close. And it's good to, if you don't have a calculator and you still need to approximate something, you can always use this method to approximate. So just so you can put an intersection point on a graph, but you don't actually know what the exact number is, you can approximate it and then put the exact value on the graph. 86, it's not a perfect square. We know that 9 squared is 81. Shouldn't do that because it looks like a fraction. 9 gives 81, 10 gives 100. So the square root of 86 is going to be closer to 9 than it is to 100. Let's say it's about 9.2 to 9.3. And you can check them out on your calcs and see if they work. You can see how close we are. Make sure you don't bugger it up like I did here. So it's between, 27 is between 25 and 26, so it's going to be somewhere between 5 and 6. Okay, arithmetic with surds. So if I square root something and then I square it, that's the same as doing nothing to it, basically. The square root of 5 squared is just going to be 5 because we're performing inverse operations on it at the same time, so it just gives us that number. So if I square root 11 and then I square it, I end up with 11. Likewise, if I square a and then I square root it, I just end up with a. So here, if we did 3 squared, we'd get 9, but the square root of 9 is 3, so we just end up with exactly the same number. If I've got two numbers and they are square rooted, we just multiply them both under the radical and keep the radical sign above. So here, root 3 times root 7 is root 3 times 7, which is root 21. Now this holds from indices. If I said a squared times b squared, we know that because they've got the same power, we can say ab squared. In actual fact here, I've got a to the half times b to the half, which is ab to the half, because square root is the same as to the power of a half. Likewise here, root a divided by root b, that's the same as a to the half on b to the half, which is a on b to the half. So here, if I've got two numbers under a square root, the number that I'm dividing by becomes the denominator, and then the first number becomes the numerator. So if I had root 35 divided by root 5, I just get root 7. Okay, I've put this table up here so that we can simplify surds. So we look at root 50 and go, okay, root 50 is not a perfect square. But what we want to do is find out if there's any perfect squares that are factors of root 50. So forget about 1 because it's pointless. Does 4 go into 50? No. Does 9? No. 16? No. 25? Yes. So what we can say is 50 is the product of 25 and 2. But we also know that the square root of 25 is 5. So I can bring it outside the square root sign, or I can just square root the 25. Actually, I'll just show you first off. You could do this. Separate it apart. Root 25 times root 2, which is 5, because the square root of 25 is 5, root 2. Same here, 27. Now, you're always, when you look for the perfect squares, you only ever go to the halfway mark. So here, the most I would go up to is 13.5. So I go, okay, does 4 go into it? No. Does 9 go into it? Yes. I wouldn't go any higher because I know 9 goes into it and 16 won't. So it's a factor. So I'll say 9 times 3. Now we know the square root of 9 is 3. So it becomes 3 root 3. This here, the square root of 9 is 3. And then I've got root 3 still under the square root. Okay, this one here looks really tricky, and it is pretty tricky, but try and find a number that will go into it first. So I look at this and go, okay, 4, will it go into 588? We can just test quickly. 588. 4s into 5 goes once, into 18 goes 4 times the remainder of 2. I get 147. So I can say that is 4 times 147, but we know that the square root of 4 is 2, so root 147. Do we stop there? Okay. Does 4 go into 147? No. 9? I don't think so, no. 16, no. 25, no. 36, no. 49. 3 times 49 is 147. So we can say 2 root 49 times 3. We know when we square root 49, we get 2 times 7 times root 3, which is 14 root 3. Now, it turns out that because we could take 14 out the front, it means that because I've taken out 14, 14 squared is also a factor of 588. 14 squared is 196. So I could have written this as root 196 times 3, because I've got 3 under the square root. The square root of 196 is 14, so I get 14 root 3. So you save yourself a few steps to get this, but you'd need to know that 196 times 3 is 588, and you'd also need to know that 196 is a perfect square. That'll take a bit of practice. You might get there one day, but it's perfectly fine to work through step by step. Okay, 7 root 243. Let's have a look. What have we got that will go into 243? Now, I think 9 will. In fact, I know 9 will. But let's say we've got something bigger. So, forget about that one. 4, no, because it's odd. 9 we know does. 16, no. 25, no. No. 49 doesn't, because 5 times 49 is 245. 64 doesn't. 81. 81 times 3 gives us 243. So I could say 7 times 81 times 3, which is the square root of 81 is 9, so 7 times 9 root 3, which is 63 root 3. Now you get to a point where you don't actually have to show all of this working. But to start off with, I'd like you to go through and show all the correct steps so that you know exactly what you're doing. Okay, here I've got 6 root 162. Now it turns out 81 goes into 162 2 times. The square root of 81 is 9, so I've got 6 times 9 root 2. That's 54 root 2. Okay, so that's it simplified. Now when you know when it's at its most simple surd, because this number under here won't have any perfect squares that can go into it. So here we've ended up with the number 2, which is also prime. Here 3, here 3, here 3. It doesn't always have to be prime. It just has to have a number that can't be a square root going into it. So root 6, that's not prime, but there's also no factors up here. Forget about 1. There's also no other factors up here of 6 that I can simplify with. Okay, whole surd. So this is where we want to make a surd that's been simplified. We want to put it back into a whole surd. So here I've got 5 root 7, but I want to put that 5 under the square root. So if I want to put the 5 under the square root, if I square root something and square it, it's exactly the same thing. So I'm not changing that 5 by squaring it and square rooting it. I'm leaving it exactly the same. The square root of 5 squared is 5. If I multiply that by root 7, 5 squared, we know is 25 times root 7. And we learnt before, if we've got 2 surds, we can just multiply what's underneath and join them together. So 7 times 25 is 175. So 5 root 7 and root 175 are the same. You could work backwards and make sure that it is the same, but we pretty much know that we haven't stuffed it up. Okay, here, that's going to be 7 squared times root 6. 7 squared is 49 times root 6. Now, who struggles with multiplying 49 times 6? I just say, what's 50 times 6? That's 300. But I only want 49 times 6, so I want 6 less. It's going to be 294. So square root 294, because that's 49 times 6. Okay, so that's a whole surd. That's everything underneath the square root. Hey, multiplying and dividing surds, we've already done it a few times, but basically what you've got to do is first you multiply them. So 7 times 5, which is root 35, and then you see if they can simplify anymore. So there's no perfect squares that go into root 35, so I leave it like that. That's going to be 3 times 11, which is 33. There's no number that goes into 33 that's a perfect square. This one here, 5 times 30 is 150. In this case, there is actually a number that goes into it that's a perfect square. 25 times 6. So if I say 25 times 6, the square root of 25 is 5, so I just get 5 root 6. So you need to first multiply them and then see if they simplify. Likewise here, you could see if they simplify first, but generally they're not going to. Like if you have a look at those, they haven't got anything that can square root. If I multiply these two, I can't simplify them yet. Multiply them together, I get 45. And then we go, okay, we know that 9 times 5 is 45, and the square root of 9 is 3. So that's 3 root 5. Now you realize why the multiplying and dividing your times tables are so important. Okay, when we divide, we just divide. That becomes a numerator, that becomes a denominator. Root 15 on 5 is root 3. Here, 70 becomes a numerator, 14 the denominator. 14 goes into 75 times, so it's just root 5. Okay, so here's a quick review of what we've just gone through. When we square root something and then square it, it's just that same thing. Likewise, if we square it and then square root it, it's the same thing. If I've got two things under a root sign multiplying, I can join them together and multiply them underneath the root sign. If I've got two things under a root sign and one's dividing the other, that's the same as putting them both under the root sign and dividing. Remember that they must have the same root sign. So if it was root 3, the cube root of 2 divided by root 5, we can't put that all under a root sign because these things are different roots. So that wouldn't simplify at all. That would just be the cube root of 2 on root 5. A surd in its simplest form is in its simplest form if the number under the square root sign has no factors that are perfect squares, apart from 1, which is what we've said a few times. To simplify a surd, take out any square factors or perfect squares. For example, root 50 is root 25 times 2, which is 5 root 2. Okay, adding and subtracting surds is very similar to adding and subtracting algebra. Forgot my words then. So here, forget about these roots at the moment. If I had 2a plus 7a minus 4a, you would say 2a plus 7a is 9a, take away 4a is 5a. Well, surds are similar in that we have like surds like we have like terms. Here, these are like surds because they've got the same thing under the square root, so I can just add them together. I've got 2 groups of root 2, and I add 7 groups of root 2. That gives me 9 groups of root 2. Subtract 4 groups of root 2. I have 5 groups of root 2. You can only add them when they have the same thing under the square root. Otherwise, they can't be added together. They're not like surds. If we have a look here, I've got 4 root 7 and 8 root 7. If I have 4 groups of root 7, I add 8 groups of root 7. I've got 12 root 7. Here I've got 3 root 5, and I take away 2 groups of root 5. I've just got 1 group of root 5. You can't do anything else. You can't add these together. Sometimes students go 12 root 12 because they add what's under the square root. You can't do that. You can only add them if they're like surds. Okay, sometimes we need to simplify first before we can add together. So you might look at this and go, okay, there's no like surds, I can't add them together. But we know that root 8 is 4 times 2, plus 7 root 2, we can't do anything with that. 32 is 16 times 2. We know that the square root of 4 is 2, so I get 2 root 2 plus 7 root 2. The square root of 16 is 4, so I get 4 root 2. And then, now they're all like surds, we can add them together. So 2 root 2 plus 7 root 2 is 9 root 2. Take away 4 root 2 is 5 root 2. Seem to remember doing that question before. Okay, you won't always have the same surds when you add and subtract. Here you can see we've got a mix. I've got 3 root 5 and 4 root 3. So just have a look and see what you can simplify. So here, that is 9 times 3 plus 3 root 5 plus 9 times 5 minus 4 root 3. The square root of 9 is 3, so I get 3 root 3 plus 3 root 5. The square root of 9 is 3 again, so I get 3 root 5. And then here I've got minus 4 root 3. Then we group together our like surds. So 3 root 3 minus 4 root 3. That's going to be minus root 3, so I'm going to put it second. Because if I add those together, 3 root 5 and 3 root 5, that gives me 6 root 5. It's not 6 root 10. Some people will do 6 root 10. Remember, it's like algebra. 3 apples plus another 3 apples gives me 6 apples. 3 groups of root 5, add another 3 groups of root 5. I have 6 groups of root 5. Okay, so now you have a crack at the questions from your textbook, exercise 2A and 2B, and see one of us teachers if you need some help. Good luck.